My next topic is no hidden variable theorems. This expression hidden variable can mean different things, has been used for different things in the literature. One meaning is any further variable assumed to exist in addition to psi, such as the Q in Bohmian mechanics, which, however, is not hidden at all. It's, you see, in Bohmian mechanics, you cannot measure the psi, but you can measure the Q. You can measure the particle position anytime you want. So it's kind of misleading to call that hidden. The other meaning of hidden variable is the assumption that every observable has an actual value already before a quantum measurement. So this is not the case in Bohmian mechanics. So in this sense, you would have to say then that Bohmian mechanics is a no hidden variables theory. Why is that? Because, for example, spin observables, sigma z, doesn't have an actual value before you do the experiment. The experiment creates the value. So now I will discuss the latter view. I will discuss the assumption that, or the idea that every observable has an actual value. So the idea, you may already know that this won't work. So the no hidden variables theorems try to prove that it cannot work. So this view is suggested by the terminology such as observable and measurement that sound like you're finding out the value of a quantity. So let us suppose, for the purpose of refuting this assumption, let us suppose for the moment that with every self-adjoint operator A, there is associated a physical quantity, VA, the actual value of the observable A. And that a quantum measurement of A simply reveals the value VA. Can it be this way? There are several no hidden variables theorems. We focus on the most important one that was first proved by Gleason in 1957, then in other or simpler ways by Specker, Bell, Koshin and Specker, Merman, and Paris. This theorem is often called the Koshin-Specker theorem, but in fact, Koshin and Specker were neither the first to do it, to prove this theorem, nor nor did they have the simplest proof. Okay. So here's what it says. Consider a Hilbert space, script H, whose dimension is at least 3, but finite. Let script A be the set of all self-adjoint operators on H, and fix a unit vector in H, psi. Then the Born distribution for this operator is, well, given by equation 1. It's kind of the obvious thing that you know very well, expressed in terms of the projections to the eigenspaces. Now, when you have several self-adjoint operators, A, B, C, which are pairwise commuting, then you can diagonalize them simultaneously. So there are joint eigenspaces, and let P, alpha, beta, gamma be the projection to such a joint eigenspace. So that's the projection to those vectors that are simultaneously eigenvector of A with eigenvalue alpha, and of B with eigenvalue beta, and of C with eigenvalue gamma. Then the joint Born distribution of all these three observables, these three self-adjoint operators at the same time, is given by equation 2. Now the theorem says the following. Consider a joint distribution of random variables, VA, for all A in A. So assume that there existed these true values. And then, of course, they would have to be random values. And they would have to have a joint distribution, because in every run of the experiment, each of these values would have a definite value at the same time. So there must be a fact about what the probability, the joint probability is of VA having a particular value and VB having a particular value and VC having some other value. Now suppose that any quantum measurement of the observable A yields just this value, VA. Suppose further that whenever two operators A and B commute, then a quantum measurement of A doesn't change the value of VB nor that of VA. So you could think that in general, a measurement of A could change the value of VB. But here we assume that if they commute, so you could do a simultaneous measurement of both of them, then the measurement of one doesn't change the value of the other. That sounds like a reasonable assumption. Then you will get disagreement with the joint Born rule in equation 2. In fact, the examples where you get this disagreement is you choose A and B that commute with each other, and as the third operator, you consider A plus B, which then automatically commutes with both A and B. Here's the proof, or an outline of the proof. So we make measurements, let's say in this order, of the observable A, B, and A plus B, and we're considering here the case that A and B commute. Then the eigenvalues of A plus B are of the form alpha plus beta, where alpha and beta are eigenvalues of A and B. Now the measurements don't, because all of these operators commute with each other, by assumption they don't change the actual values of these observables. Now the joint Born rule would imply, because the whenever A in the joint Born rule assumes the value alpha and B assumes the value beta, then A plus B has to assume the value alpha plus beta. That implies that the V value, the true value of the observable for A plus B, has to be the V of A plus the V of B. But this is impossible. Now that's kind of the mathematical key part of the proof, but this part I will omit. I will just report this result as a lemma. When the dimension of the Hilbert space is at least 3 but finite, then there isn't even any mapping that would associate with every self-adjoint operator a value in the spectrum of this operator. That means one of its eigenvalues and be additive in the sense that whenever two operators commute, the value of the sum, or the value associated with the sum, is the sum of the individual values. So the upshot of this reasoning is it's not convincingly possible that there is an actual value VA for every observable A. So that's the content of the no hidden variable theorem. And now I already said that in Bohmian mechanics, you don't have actual values for every observable. So this theorem doesn't do anything like exclude Bohmian mechanics. But you might think, well, still in Bohmian mechanics, after all, it's a deterministic theory, right? So the outcome of the experiment is predetermined. It's a function of the initial data. Actually, it's a function of the initial configuration of the particle, the initial configuration of the apparatus, the wave function of the particle, and the wave function of the apparatus. That's a fact. So why isn't the outcome then, if it's such a function, not one of these VAs? Because it depends also on the initial wave function and configuration of the apparatus, and not just on the observable that's being measured. Here's a concrete example. Here are two different experiments that are quantum measurements of the same observable. The observable here is sigma z. And the first experiment is just a Stern-Gerlach experiment in the z direction. And the other one is a slight modification of that. You invert the polarity of the magnet. Okay, you make sure that the upper part is actually the south pole and the lower part is the north pole. And then what happens if you send a wave packet through this magnetic field, then the spin up part will move downwards and the spin down part will move upwards. And then you do the following. If you detect the particle in the upper packet, you call it spin down. If you detect the particle in the lower packet, you call the result spin up. Now, then actually the probability distribution of up and down is exactly the same as in the other experiment. So this experiment is also a quantum measurement of the observable sigma z. But when you apply it to a particular initial wave function psi of the particle and particular initial position x of the particle, then actually these two experiments may have different outcomes. This phenomenon is sometimes called contextuality, that different experiments measuring the same observable can have different outcomes. That may sound strange, but actually, when you realize that the word measure doesn't mean measure, it's not a measurement in the literal sense, then what's strange about it? Okay, in the end, the result is that the result of an experiment depends on the experiment, as Dürr and co-authors once nicely put it. So, and if you look at it this way, then there is no mystery at all. The result depends on which of the two experiments you do and not just on the observable. So you can have two different experiments belonging to the same observable. They may yield different results, but they do yield the same probability distribution of results. And of course, well, if you toss two different coins, they have the same probability distribution of heads and tails, but they may well yield different outcomes, of course. My next topic is quantum logic. Quantum logic, this term means different things in the literature. It can mean a certain piece of mathematics that is rather pretty, a certain analogy between two formalisms that is rather limited, and a certain philosophical idea that is rather misguided. Let me explain. Maybe I should first try to give some definition of logic. I would say logic is the collection of those statements and rules that are valid in every conceivable universe and every conceivable situation. Now, for logic, you have rules for how to operate with connectives and or not. These rules are people have summarized them in the smallest possible number of axioms and called that Boolean algebra. So here I've listed these axioms. I will not go through these axioms. Let me just say, so here the mathematical definition of Boolean algebra is to have some set whose elements can be combined. You can form, for any elements, you can form A wedge B or A VB or non-A, and then you have these rules, commutative, what have you, okay, complementation laws, distributive laws. Okay, so these rules actually agree with the rules of logic. When you read the wedge symbol as meaning and, you understand the ABC as being statements, the V symbol as meaning or, and this hook symbol as meaning not. That's not the only possible interpretation or situation in which Boolean algebras apply. These rules also apply when A, B, C mean subsets of some basic set omega, and the wedge symbol means intersection, the V symbol means union, and this negation symbol, the hook, means the complement. Okay, then you have the same rules. Okay, now there's another situation where you have the same rules or almost the same rules. That A, B, C mean subspaces of Hilbert space. Okay, technically speaking, we would have to say closed subspaces, but okay, that's a fine detail. Actually, in finite dimension, if your Hilbert space has finite dimension, then every subspace is automatically closed. So let's talk about the subspaces. And let's say the wedge symbol means the intersection of two subspaces, which is then another subspace automatically. The V symbol means the smallest subspace that contains both A and B. Or in other words, if you have two subspaces, say two one-dimensional subspaces, you form the union that is not itself a subspace, then you form the span of that, and actually then you form the closure of that, then you get a closed subspace. So that's the smallest closed subspace that contains both A and B. The hook symbol means orthogonal complement. So that means the set of all vectors that are orthogonal to every element of A. Okay, so the orthogonal complement. Good. In these, the zero symbol, which was kind of the statement that is always false, becomes the zero subspace. The one statement, the one symbol, the statement corresponding to the statement that's always true, then is now interpreted as the full subspace, the full Hilbert space. Then all axioms of a Boolean algebra except distributivity are satisfied. Such a thing is called an orthomodular lattice, or simply a lattice. In other words, a distributive lattice is a Boolean algebra, and the closed subspaces of a Hilbert space form a non-distributive lattice. So that's pretty mathematics. If you're into mathematics, what's nice here is that you have kind of similar structures going on in different contexts. And that proves that you've done for subsets or for logic, you can reuse them for subspaces of Hilbert space. Okay, now I said the second meaning of quantum logic is a certain analogy. Okay, what is the analogy here? The analogy is between the lattice of subspaces of a Hilbert space and the Boolean algebra of logic. Both are orthomodular lattices. Just one is distributive and the other is non-distributive. Okay, so actually the logic is distributive and the subspaces are non-distributive. So some authors call elements of this lattice, which really are subspaces, a proposition or a yes-no question, because they have in mind, you could do a quantum measurement of the projection operator to this subspace, and the possible outcomes are 0 or 1, and let's call that no or yes. And correspondingly, some authors call this, this lattice of all subspaces quantum logic, or a quantum logic, because it's a certain set of things that have operations wedge and V and hook, and they satisfy similar rules. Now, this analogy, there is a certain analogy, of course, both are orthomodular lattices, but the analogy is limited. Here's why. Here are two examples where the analogy doesn't fit. Consider a spinner in two-dimensional spin space, and consider the following words. Psi lies in the one-dimensional subspace through the spinner up. Okay, a particular one-dimensional subspace. Let me call these words P. So P sounds like a proposition, right? Its negation is Psi does not lie in this one-dimensional subspace, which means it lies in Hilbert space without this one-dimensional subspace. Whereas the orthogonal complement of the subspace is this subspace, is the all multiples of the down spinner. Okay, so the usual notion of negation of a proposition does not correspond to the notion of negation in this lattice. Let me say that again in different words. The negation of spin is up is not spin is down, but spin is in any direction but up. So this is where the analogy actually doesn't quite fit. Here's another example. in Wheeler's delayed choice experiment. Remember, you had that the two wave packets, they come together, they overlap here, and then they separate again, and then they run into two counters. And you had the possibility to put a plate P in the interference region. Now let's say you don't put a plate there. You just consider this evolution of wave packets. But then you have a subspace A of waves passing through the upper slit, and that evolves to the subspace A prime of waves arriving at the lower counter, and vice versa. And it's natural now when you have this at two different times to identify this the subspace here with the subspace there, and both of them with the proposition the particle passed through the upper slit. But that means to commit Wheeler's fallacy. What was Wheeler's fallacy? It was that you conclude that if the particle is detected in the lower counter, it must have gone through the upper slit. That was something that's actually not true for the Bohmian particle. So if you take particle really seriously, literally, if particle means particle, then it's not true. So, according to, well, when you identify subspaces of Hilbert space with propositions, then it's very easy, very tempting to slide into this identification as Wheeler did, of identifying the proposition the particle passed through the upper slit with the subspace of waves that arrive down here. Then I said quantum logic also sometimes referred to a certain philosophical idea, the idea that somehow that ordinary logic as we know it, is false, and that a different kind of logic with different rules applies in quantum physics, a quantum logic. Now I called this a misguided philosophical idea. Why is that misguided? Because logic is, by definition, what is true in every conceivable situation. It cannot depend on physical laws. It cannot be revised by empirical science. It could only be that something that we thought was a law of logic, a rule of logic, is actually incorrect. But if that were so, then, well, there should be mathematical examples of that and not empirical ones. So logic is not the kind of thing that depends on empirical findings, that depends on physical laws. And it was once nicely put by philosopher Tim Maudlin, who said, there is no point in arguing with somebody who does not believe in logic. So that means if you entertain the idea that logic might be wrong, then you're kind of lost on the wrong track. And that's the slides that I have for today. Thank you very much for your attention. And maybe there are questions.
Hello. Can you hear me?
Okay.
Yeah. I was asking about many world theories, like this. When wave function make branch of the measurement, I was thinking that these whole things, when we say it's based on basically linearity of Schrodinger equation. But thing is, if you will take it seriously, very seriously, yeah, okay, that's many world is very serious theory or possible that I think it will conflict with general theory of relativity.
Conflict with what? I couldn't understand what you said.
General theory of relativity.
Relativity?
GTR, yes.
Why do you think it would conflict with relativity?
For I mean, first guess that, like, suppose this, we do anything, we write a Schrodinger equation, and Schrodinger equation looks very innocent, very nice, but when we write this equation, we take the operator differential, what is involved in that, that is in flat space. So for me, philosophically, if we say, when we write theory, we presume that there is a background before existing there. So then we will write theory. If we will follow the old classical philosophy of doing physics, that there is a background and we write theory. We have theory in some background is pre-existing, like space-time here. So when we write down the very nice form of Schrodinger equation, what looks very, what looks linear, what does look very neat and clean, that equation, what people often show this equation, often present this equation, but those equations are written in metric, mostly Euclidean or Minkowski. Then we presume that the theory we are taking, theory we're doing, or physics we are doing, it is in flat space time. So we presume that background is flat. So the pre-existence of background is there. Now we do some theory and experiment, whatever, in pre-existing background, and we claim that when we make measurement, then a different world will separate out from this. So what does world mean? Is universe, or this like all observable? What is? If it is universe, then it is not possible. It means like you are saying that you're making measurement in flat space time, and then there will come out a different universe which has different geometry. So and first thing this, and second thing, if such things universe is separating out through measurement, there must be interaction between them, because like both are weighted by heavy mass and energy or whatever. This was my concern.
Okay, so let me give several elements that are relevant here. First of all, when you take the Schrodinger equation, replace it by some relativistic equation, such as the Dirac equation, okay, you can do that, and you can set up some version of this law for the matter density as well, if you want, that is Lorentz invariant. So that can be done. That's not a problem. Also, if you want a curved space-time, okay, say you have a curved background, you want to do quantum mechanics in a curved background, you can also consider, let's say, the Dirac equation for n particles in a curved background. It's kind of, and you could also define some m function for that. So that is also possible. That is not a problem. Now, doing full quantum field theory in curved space-time is not easy, is a delicate thing with many open questions. But I see no particular obstacle that would connect to a many worlds view in a stronger way, or put a stronger obstacle for a many worlds view than for any other view. Then you might think, okay, really, I want to have not a background metric, I want to have a quantized metric. So we go to quantum gravity. Well, there, of course, then things become difficult. There is no accepted theory of quantum gravity, and I'm not sure if there is even any approach to quantum gravity that fully works. Okay, so that's just something that, as of 2020, we don't know how it works. But again, I don't see any particular reason to think that that the many worlds view would have more trouble with that than other interpretations of quantum mechanics. Oh,
Yeah,
Albert.
we will talk about
Okay.
it later. Yeah, I think. Yeah.
Yeah. Okay. Albert. I I uh, I can hardly hear you. Can you turn your microphone louder?
In the Bohmian
Okay.
theory, the phase is used to define the velocities, but the phase of a complex number is not well defined at the origin at zero, because it can be anything and you still get zero. Is this a problem, or in the theory can there be anomalous situations, singular points where the velocity is not well defined at a node of the wave function?
In short, it's not a problem. Here's what happens. Yes, exactly as you say, at any point where psi is zero, the velocity is not defined. So if you compute your trajectories by solving the equation of motion, whenever your trajectory runs into a node of the wave function, a point where psi is zero, then the differential equation breaks down. You cannot extend it any further. um, so the question is, how often does that happen? The answer is that concerns that happens with some trajectories, but they form a set of measure zero. In other words, it has probability zero that that a trajectory would ever hit such a node. Okay, so it's not a problem for the theory. The theory is kind of as well defined as you could hope it would be.
I see. So so most trajectories miss these nodes, let's say.
That's right.
But I mean, are there? Let's say if we were to play a game, can one cook up situations, special wave functions where perhaps interesting things might occur, where where I don't know, maybe you have a line of nodes or something like this.
You can have many nodes. For example, you could choose your wave function at t equals zero to have compact support. That means you just have a bounded set where the wave function is non-zero, and it's zero everywhere around it, almost everywhere, okay, except for some finite volume. So then kind of most points then would be nodes of the wave function. And then you can solve the Schrödinger equation for positive and negative times. So you'd have some wave function that evolves towards then that has many, many nodes and then goes on. But actually these nodes, most of these nodes would be just at time zero, not at positive or negative times. So you would have fewer nodes at positive or negative times. And what would happen is that that the Bohmian trajectories all pass through the region, or with probability 1. They pass through the region where the wave function is non-zero and then go apart again. So the statement is that with probability 1, your trajectory exists for all times from -infinity to +infinity without ever hitting a node.
The same is true generically for all wave functions. It's not possible to think of a very special situation. Like, I'm not asking, like in most cases it's true. I'm asking, if I wanted to try and break the theory, or see where its limits is, can I cook up a very strange Hamiltonian or a very strange wave function where that wasn't true, where there was actually a non-zero probability? So some trajectories do pass through a region of zero, and then they do
So it has been proved for all smooth wave functions, functions that are infinitely often differentiable. Okay, so that I guess you would expect that if you try to prepare some wave function, it would be a smooth wave function.
Okay. Okay, thanks.